Okay, so the question is to solve the old shortest path problem, we need to come up with a recursive definition of the problem such that we can efficiently compute it. And the question, of course, is what recursion to come up with. And there are many natural recursive definitions for shortest path that one can try, but they don't really work. They don't speed up over what we have already. So you need to come up with a slightly counterintuitive recursion that turns out to work. And here's the idea. The idea is that we look on the path from, let's say, U to V. Think about all the vertices being number 1 to n, right? So there are numbers, we just need some order on the vertices. And now we look on the vertices between these two nodes, and we look on the indices written on the vertices, right? This might be vertex 7, this might be vertex 9, vertex 13, and so on and so forth. Right? Now I'm going to care about the largest number written on this path, in the middle, intermediate. So not the first one, not the last one. The first vertex, the last vertex can be, their indices might be quite large. I don't care. I care only about the indices in the middle, and I care about the largest index. This is going to be the index that determines this path intuitively. Okay, so now we're going to define this quantity, which is distance ij and k, where it's it's the shortest path between the vertex I and the vertex j, where all the vertices in the middle have numbering smaller or equal than k. Okay, so let's see how this definition play out in this graph. So dij0 means that all the intermediate vertices between I and j are at most 0. Since all the vertices are between 1 and 8, means that this is just the price of the edge. If there is an edge, it's going to be the price of the edge. If there is no edge, it's going to be infinity. In our specific case, there is an edge between I and j. Its price is 100, so this is going to be 100. Okay. ij1. What does ij1 means? It means we want the path between I and j that can use an intermediate vertex with index at most 1. Well, there's only one such vertex, 1 of course. So this path is this path, right? Going 4 and 5. Okay, so this is going to be 9. Okay, next. dij2. We are allowed to use the vertices 1 and 2. In this case, we will go to 1, then we'll go to 2, and then we'll go to j. Right? Of course, this is a very artificial example, so we will use all the numbers somehow, which is not usually what would happen. And in this case, we will get 4 to 10, so 16. That's not the shortest one, right? That was my mistake. We're allowed to use 2, so the cheapest path between, in fact, is this one. I to 2 and 2 to j, so 1 and 10. Now I'm very confused because, I see. That's okay. That's very good because it demonstrates that definition is not easy. Okay, my path is going to go from I, this is I. The path would go from I to 2. From 2 it would go to 1, and from 1 it would go to j. Right, so 1, 2, 5. This is indeed 8. Okay, and the last one is ij3, which means that I can use any intermediate vertices, which means that I can just look for the shortest path. And in this case, this is going to be 1, this, and this. Right? Okay, and this is going to be 3. And I have no clue why the slide says 5, because this is 2. Sorry. 1, 2, 1, 1. So yes, this is 5. Okay. So this is the definition. Now, why is the definition useful? Well, think about the path between I and j, where the largest index is k, and in fact vertex k appears in the middle of the path, right? So it's like that, right? But then the recursive definition here is very natural, right? Because I can say, well, give me the shortest path between I and k by a path that maximum vertex is smaller than k minus 1, right? And give me the path between k and j, again, that the maximum vertex is smaller than k minus 1, and put them together, right? So this definition, bizarre as it may be, gives a natural rise to a recursive definition. So let's do that. Okay, this is just going through the example, but without my silly mistakes. Okay, let's see an example, a question. What is dij2 in this graph? Let's see. So dij2 means that we are allowed to use vertex 1 and 2. We are not allowed to use vertex 3, right? And we're going from I to j. So let's see. Well, so there are the only, okay, so now we have to just go over the possibilities. And in particular, in this graph, you can just use the extra, right? So let's do that. So this would be distance 5, right, by the extra. And now we have this, so this would be 7, right? And the cheapest way is 5, right? So this is going to be the cheapest. So 5, 7, 5, you know, it's 12. If I did my calculation correctly. Okay? So that's this definition of intermediate, shortest path with intermediate vertices. Okay, so as I said, this now gives rise to a natural way to decompose the path. Either there is no, in the shortest path between I and j, there is no kth vertex in the middle, so then it's just the distance between an I and j using maximum index k minus 1. Or alternatively, the kth vertex does appear, but then we have to go from I to k, where the maximum vertex is smaller than k minus 1, and then go from the kth vertex into j, where the maximum vertex is smaller than k minus 1. Okay? And we take those two options and we take the minimum. Right, and now we need to handle the base case. So the base case is dij0, as I said, is just the price of the edge, if the edge exists in the graph. If the edge does not exist in the graph, it's infinity. And the correctness is, you know, we just argue to it. Either it contains the kth vertex, the shortest path, or it doesn't. In either case, one of those two choices holds. So this recursive definition indeed works. And, okay, so we now have this recursive definition. We have two worries about negative cycles, but you know, it's not going to be very difficult to worry about, to discover negative cycle, because a negative cycle would just imply that dkk, right, at k minus 1, for some vertex, this is going to be smaller than 0, right? Going from kth vertex into itself is going to be negative, and then we'll take a negative cycle, and then we can just stop. Alternatively, you know, we have Bellman-Ford can detect negative cycles for us, so we can just run Bellman-Ford as a way to detect negative cycle first, but it's simpler to just, you know, in the end of the execution, just check if we have a negative cycles computed. Okay, so now we have a recursive function for computing the shortest path between all pairs of vertices. It's not immediately obvious what would be the running time if we now just do memorization, so let's figure this out. So we have three parameters, I, j, and k. They can all go between 1 and n. So we're going to have n cubed distinct calls. That seems bad. But the nice thing about this is that computing the recursion takes constant time, ignoring the price of the recursive calls, of course. Right? So If I throw this into memorization, or do explosive memorization or dynamic program directly, this is going to be O of n cubed time, right? Which is a big improvement, right? Because previously all we had was n to the fourth if there was negative edges. So the next step is to convert this into a dynamic program, which we will do next.